Okay, so today we start this lecture 23, in which we will continue from the last lecture, in which we started about description of ionic solid structure based on face centered cubic packing. So just to give you a recap, we discussed structures based on FCC packing of, we started discussing structures based on FCC packing of anions, and there we first started with the rock salt structure, which is basically based on NaCl based compounds, which make in which chlorine makes FCC lattice and sodium ions occupy the octahedral interstices, all of them. So 100% occupancy of interstices, and this is based on radius ratios. So there are a variety of oxides which follow this kind of structure like FeO, NiO, MgO and so on and so forth. Second structure that we looked at was sphalerite or zinc blend structure, which is based on zinc sulfide. This structure is again sulfur makes FCC lattice and zinc occupies the tetrahedral sites, and you can see that since FCC lattice has 8 tetrahedral sites, that is 2 per ion, as a result only half of the tetrahedral sites are filled. So you can consider both NaCl and zinc sulfide as if there are 2 interpenetrating FCC lattices. In case of NaCl, the FCC lattice of sodium is shifted by a vector half 0 0, whereas with respect to chlorine lattice, whereas in zinc sulfide the FCC lattice made by zinc is shifted by a vector 1 by 4, 1 by 4, 1 by 4 with respect to sulfur lattice. And then we started discussing about fluorite structure. And this also includes fluorides or antifluoride. So this we will discuss while we discuss fluoride structure. So we started discussing this. So basically okay, so fluoride structure basically is based on compound. So parent compound is CaF2. Now this is based on your radius ratio. So here basically RCa to RF is such that you tend to follow. So this is close to, I think it's between 0.7 to 0.8 depending upon the radius, but I think it's about 0.8, closer to 0.8. Nevertheless, it falls in the boundary of octahedral to cubic coordination. So you can check up the radiuses online. It falls on the boundary of octahedral and cubic coordination. As a result, what happens is that the cation coordination number is 8. So we discussed that if the cation coordination number is 8, one possibility is to have a cesium chloride kind of structure. So cesium chloride could be a possibility where cesium can be coordinated, where fluorine can 8 of fluorine atoms will surround 1 calcium atom. However, if you have that kind of structure, the problem is calcium, the fluorine will also be surrounded by 8 calcium atoms, which is not possible because of bond strength check, because we can see that if you do the bond strength, then bond strengths of cations and anions should be equal, they should balance each other. So if you look at the for calcium, for example, the valence of calcium is 2 and the coordination is 8. So this is 1 by 4. In case of fluorine, the valence is 1, coordination number must be equal to, so this must be equal to 1 by 4. So coordination number of fluorine must be equal to 4. As a result, the CSCl is not a possibility. Okay. So, we will see CSL structure later on, but basically it is a structure in which both cesium and chlorine are cubically coordinated. So, the way this structure works out is in this fashion. So, you make a FCC lattice of, so I am just going to draw the top view here. Okay. So, if I draw the top view, so remember coordination numbers, calcium coordination number is 8 and fluorine coordination number is 4. So, fluorine is tetrahedrally coordinated. This is cubic. So, let us just draw these a top view of the lattice here. So, here what I am drawing are these are all. So, this is here is calcium atom. Okay. So, these are all calcium atom. This is at 0 1, this is at half, this is at 0 1, this is at half, 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 0 1, 0 1, 0 1. Okay. So, calcium makes a FCC lattice here, and the zinc and the fluorine atom goes here, here, here and here, and the coordinates which are going to be filled are 1 by 4 and 3 by 4. All the tetrahedral sites are filled here. Now, this we have drawn on the basis of cation forming a lattice and anion going to the tetrahedral interstices. However, if you want to look at the structure in the perspective of what will happen if cations form the lattice, then you need to consider a unit cell in a different manner. So, let us say I draw a unit cell which is something like that. Now, this is a bit complex unit cell. So, I need to divide this unit cell into 8 unit cells. So, what I do is that this is the problem with the drawing. The drawing should be done in such a manner so that we should not get parallel lines. Okay. And let us say I make these unit cells which are and we need to create a division in the middle as well. So, the middle division is going to be created in this fashion. And there is going to be a boundary here as well. So, you have 8 of these unit cells. Okay. Now, you start filling in the fluorine. These are all fluorine atoms. and I needed to draw one line there and one line here, so that I have one atom at the center, also one here. So, is everything complete? No, these are not complete here. Okay. So, how many unit cells now you have? You have 8 cubes formed by fluorine. So, these are all fluorine ones. Okay. This is fluorine. So, this was fluorine here. Now, you need to put calcium in it. So, the problem is these are 8 unit cells, you have 8 fluorine atoms. You can only put 4 fluorine in there. So, the way 4 fluorines get in is like this. So, this is the first unit cell, the center of this unit cell is, this is first fluorine atom, the second fluorine atom is this, calcium atom, yeah, I am sorry, yeah, thank you. This is calcium atom, and the other 2 calcium atoms go in these unit cells. So, center of this and this. So, this is how you are going to make a calcium fluoride structure. So, this structure is basically you can see now what you can do is that if you take the plan view, now instead of keeping the lattice corner at calcium, you keep the lattice corner at this site. Let us say I keep the lattice corner at this site. So, I need to go here, I need to come here, I need to go there, and then, and the way you then, so this will be another chlorine atom, fluorine, this will be another fluorine, this will be another fluorine, and this will be another fluorine. So, and then you need to create, so these are at 1 by 4, 1 by 4 and 3 by 4. Okay. So, you have only 3 positions, you need to create another position which is another 1 by 4. So, you need to stack 2 layers of fluorine in such a fashion, so that you have first one at 1 by 4, second one at 3 by 4, the next one is at again 1 by 4, and when you make 1 by 4 as 0, the 3 by 4 becomes half, right. So, the position will be 0 half 0 or 0 half 1. So, all the atoms will be arranged. So, these will make 8 cubes, and then you can see the position of these atoms. This is at 0 1, this is at 0 1. So, this will become quarter, right. So, when you make these distinctions here, so sorry, there is a bit of a, yeah. So, you can see that these 2 atoms go in this fashion, these 2 atoms will go in this fashion. So, if you take the top view will be there is a mistake I have made here. I think this atom will, sorry, let me just rub it out, let me remove this blue atom here. So, you have one blue there. So, one blue is at 0 1, second blue. So, this, let us say if this is the blue here, the second blue will come here, okay, because 0 1 half, and now we are looking at the top view, right, and the third blue will go it is at the half position. So, it will go here, and the fourth one will come here on top, right diagonally. So, 2 will go this way, 2 will go that way, they will make a so in the first unit cell here. So, I did not draw that very well. So, this is my first one, the second one will come directly opposite here at the center of this unit cell. So, these 2 will go diagonally there, you can see diagonal arrangement, and these 2 will come diagonally here, just like you have in zinc sulfide lattice. So, that was a modification we can make. So, let me just reiterate what you have here is I will just maybe redo it. Okay. So, if you look at this bigger unit cell which is now made by calcium, okay. So, this calcium will be all of these are at 1 by 4 3 by 4, 1 by 4 3 by 4, 1 by 4 3 by 4, 1 by 4 3 by 4 and then 1 by 4 3 by 4. Okay. These are at 0 1. When you convert these two, so if I now take it away, okay, if I now take it away, make this unit cell like this, just the top view, okay, just the top view, and then now I put these here. If I convert 1 by 4 to 0, then the central one will become at, so 0, half and then 1. Here you will have again 0, half, 1. These will also be 0, half, 1. So, all of these will be all of these will be 0, half and 1, all of these, right, 0, half, 1, 0, half, 1, 0, half, 1, 0, half, 1, 0, comma, half, comma, 1. So, these are at Z positions, okay. So, when you convert the 1 by 4 into 0, the 0 which is there becomes minus 1 by 4, right. Minus 1 by 4 is equivalent to 3 by 4 and 1 will become, so 1 will become 3 by 4 also. So, this is at atom which you put here, which is the blue one. The blue ones are fluorine, right. So, we have converted half quarter to 0. So, which means we are subtracting by 1 quarter, okay. So, when we subtract by 1 quarter, this will become minus 1 by 4, this will become 3 by 4 and this half 1 will become, you had another, so this is at half, this half 1 will become 3 quarter, no, half minus 1 quarter, 1 quarter, this will become 1 quarter, this will become minus 1 by 4, 3. So, we can take only one of them, we do not have to take both of them because one is below the unit cell, another is within the unit cell. So, this position will be, so you can modify this as only 3 by 4, only 3 by 4. So, basically you have 2 atoms sitting here at 3 by 4 and 2 atoms sitting diagonally at 1 by 4. So, when you construct that bigger unit cell, the bigger unit cell will, now you understand the bigger unit cell, you have let us say I start from here. Okay. Okay. All right. Now we draw this in 3D. So, my fluorine was the red one, these are fluorines, these are again fluorines, and these are fluorine again. All right. So, there are 2 atoms at, so if you look at the previous position, 2 at 1 by 4, 2 at 3 by 4. You can say one in the back unit cell will be, this is at 3 by 4 and one in the front will be at 3 by 4, and then one in this will be at 1 by 4 and one in that will be at 1 by 4, 1 by 4. These 2 are at 1 by 4, Z is equal to 1 by, so this is Z, okay. So, this is Z is equal to 1 by 4, this is Z is equal to 1 by 4, this is 3 by 4. XY coordinates are different. In this case, the XY will be, so if you take half of it, if you take this as an origin, for example, coordinate of, so and this is, let us say X, this is Y, coordinate of this will be 1 by 4, 3 by 4 and 1 by 4. Coordinate of this will be 3 by 4, 1 by 4 and 1 by 4, and accordingly you can take the coordinate of that. This one will be 3 by 4, 3 by 4, 3 by 4. The coordinate of this will be 1 by 4, 1 by 4, 3 by 4. So, this will be the bigger unit cell which is constructed by fluorine atoms. So, this is fluorine, this is calcium. Okay. So, this is how the coordination is. Now, you can see that each fluorine is coordinated by 8 of calcium and each 4 of calcium and each calcium is coordinated by 8 of fluorine. So, this is how the coordination will go, and you can see that only half of the tetrahedral voids are or cubic voids are occupied there. You can see only, since there are 8 cubes, only half of the cubes are filled. So, only half of the cubic sites are filled, all right. So, now this calcium fluorite structure is followed by a variety of materials. There are a lot of fluorides which follow this structure. So, CaF2, but you also have ZrO2, UO2 and various other oxides follow this structure, okay. So, these are all ionically bonded solids. Now, another compound in this series is called as antifluorite. So, I am just going to draw a top view there, I am not going to draw the, so antifluorite is basically, so if CaF2 was AX2, this becomes A2X, okay, things like Na2O, okay. These follow this structure which is opposite to what we saw there. So, if you have a unit cell, I am just going to draw a top view, right, 3D you can work out yourself, which we have drawn in case of the previous. So, in this case now, this will be the this is anion X. So, this is at 0 1, this is at half, 0 1, half, 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 0 1, sorry, 0 1, 0 1, 0 1 and half. So, these are all X atoms. The A atoms go in these positions. Okay. So, A atoms will be now at 1 by 4, 3 by 4. So, this is A, this is A, this is A, all of them are at 1 by 4 and 3 by 4. That is the opposite of CaF2 structure. So, you can see that. Now, what does this structure? So, lattice type in both of these structure is FCC, it is a FCC lattice. If you look at the previous structure, it is like, so we have seen that calcium makes FCC lattice, right. Calcium surely makes FCC lattice, but for fluorine you are seeing as if there are 8 cubes, it is like two FCC lattices of fluorine put into each other. So, one lattice of fluorine is, if I mark the atoms, 1, 1, 1, 1, 1, 1, and those at faces 1. So, 1, 2, 3, 4 and 1. This is the first lattice of fluorine. Where is the second lattice of fluorine? Second lattice of fluorine is this, which is second, shifted by not 1/4, half 0 0 vector, right. So, this was the corner one at, so you can figure out yourself, right. This is 1. So, all the atoms which are at edges and the body center will be at sorry, number 2. So, this is 2, 2, 2, 2. So, this is the second lattice of. So, basically you have first lattice of fluorine, second lattice is shifted by half 0 0 vector, they make 8 cubes together, they give you 8 cubes, and within those cubes you have these cubical arrangement of calcium atoms. Similarly here, so it would be again FCC lattice, but instead of fluorine making 2 FCC lattices, now the sodium will make 2 FCC lattices, and anion will make only 1 FCC lattice. So, lattice type is FCC. Okay. In case of fluoride, motif will be at fluorine at 0 0 0 and half 0 0, and calcium will be at, and then it will also make. So, all three will make FCC lattices, you have 3 atoms. In this case, motif will be A at 0 0 0 and half 0 0, and X will go to. So, basically it is a network of 3 interpenetrating FCC lattices. In the first case 2 of anion, 1 of cation, in the second case 2 of cation, 1 of anion, alright. So, this is how you make anti-fluoride structure, which is again a FCC based, again based on FCC packing of anions. Okay. Now, what we will do is that we will look at another structure which is called as Spinel structure. Spinel is a compound which has a formula Ab2O4. Okay. It is again based on FCC packing of anions, and if it is based on FCC packing of anions, you can see that for 4 oxygen you will have 8 tetrahedral and 4 octahedral interstices per formula unit, right? Per formula unit. Each formula has 4 oxygen atoms. This will give you 8 tetrahedral and 4 octahedral. Number of cations that you have are only 3. So, all the interstices are not going to be filled. You will have partial filling of interstices, okay, because it is not possible. You have total of 12 interstices and you have only of 3 cations. So, how do you fill them? Well, in the normal variant of, so there is a variant of a spinel which is called as normal spinel. In case of normal spinel structure, what you have is the A, you have basically you can say partial filling of interstices. All the A atoms go to tetrahedral sites and all the B atoms go to octahedral sites. Okay.
So is this a convention sort of thing?
Yeah, it's a convention. I mean, because A and B have different sizes. Because A and B are not same cations, they are different cations, they have different sizes, so they prefer to go to different sites. So as a result, you can write this oxide in a different manner. AB2O4 can be written as if it's a mixture of AO dot B2O3. So there is a sublattice of AO, there is a sublattice of B2, they are mixed into each other to give you what is AB2O4. So it turns out that all the oxygen atom will make FCC lattices, and A will go to tetrahedral sites and B will go to octahedral sites. There is another variant of this which is called an inverse spinel. In inverse spinel, it's other way around, it's different. So AB2O4 can be written as BABO4. The B, one of the B atom goes to tetrahedral sites and the A and B atoms go to octahedral sites. So these are two variants of spinels, normal and inverse. Examples of normal spinels are things like ZnFe2O4, MgAl2O4, COAl2O4, cobalt aluminate, magnesium aluminate, and so on and so forth. And the example of these are inverse spinels are Fe3O4, NiFe2O4, COFe2O4. So most of the ferrites make this kind of structure, inverse spinel. So you can see that you can write this Fe3O4 as FeO dot Fe2O3. NiFe2O4 can be written as NiO dot Fe2O3, and so on and so forth. Similarly here you can write this as MgO dot Al2O3, COO dot Al2O3, and so on and so forth. So we will stop here and then we will get back to the structure of a spinel in the next lecture.